For introduction and background, CFD analysis involves solving the governing equation for fluid flow and heat transfer using advanced computational models. This approach allows for detailed investigation of the intricate details of heat transport and the interaction between fluid and solids inside the heat exchanger. The problem statement for this computational fluid dynamic project entails conducting an in-depth analysis of flow and heat transfer within a two-dimensional airflow through a compact fin and tube heat exchanger. Next, for the objective, first, developing steady and incompressible flow model using the Fluent CFD simulation software. Second, visualize velocity and temperature variation within the heat exchanger. Third, to investigate the heat transfer coefficient and pressure drop under varying conditions such as a flow rate, tube arrangement, material type, and tube diameter. Next, for scope. The scope of this project, analyzing flow and heat transfer in a compact fin and tube heat exchanger using the Fluent software. Then, for the literature review, fin and tube heat exchanger are widely used in various industrial applications due to their compact design and high heat transfer efficiency. Computational fluid dynamics has become a powerful tool for analyzing the flow and heat transfer characteristics of the heat exchanger. Next, heat transfer enhancement technique. First, fin geometry optimization. Optimizing fin geometry has been shown to improve heat transfer and reduce pressure drop. Second, inclined fins. Inclining fins has been found to enhance heat transfer and reduce pressure drop.
We're starting with the geometry diagram. This is the inline diagram at 12 mm and this is the staggered 12 mm. But for the meshing, this is 5 different element size we test. And there is the number for inline and there is the element number for staggered. And for the meshings, starting with the inflation layer, we did first layer thickness with max layer of 20 and gross rate 1.2. And for the edge sizing, we do number of division of hundreds, gross rate 1.2. For the mesh quality, the element size is 0.005 and we change smoothing to high. The result of the node is 45,655 and for the element size is 44,632. And this is the maximum and minimum value of skewness, orthogonal quality, and aspect ratio. For the mesh independency test, the purpose is to ensure simulation results are accurate and reliable, and it's important because the coarse mesh may lead to inaccuracies and fine mesh increase computational costs. This is 5 different mesh size with 5 different number of element and with 5 different mesh view. Decrease mesh size increase the number of element. High resolution of the model achieved with smaller mesh size. Greater computational demand due to increased element. So at this point, indicate mesh independence. So we conclude we are choosing mesh tree for its balance between accuracy and computational costs. For minimal changes in result were observed. This indicate that further refinement beyond mesh tree does not significantly affect the outcome.
So to start the simulation, we first by switching on double precision for the solver options and change the number to 2. As for the general setup, the parameters are set as pressure-based with absolute velocity formulation, steady time, as well as planar to d-space. So since in this case, the types of the governing equations to be solved will be determined with the consideration of the viscous effect as well as turbulent effect, we switch the viscous to laminar and turning on the energy and the models. So after the general setup is done, we then modify the material properties. So there are 4 materials involved in this simulation: A, aluminium, CNT, as well as copper. So the material properties are set based on this table shown. So after the material properties are done, we then move on to modify the boundary conditions for the flow domain. So for the inlet, we change the parameters for inlet velocity as well as temperature to 1.8 meter per second and 300.15 Kelvin respectively. As for outlet, we change the temperature to 300.15 Kelvin, and tube, we apply temperature as thermal conditions with temperature of 373.15 Kelvin with aluminum as material. As for the wall, we also use temperature as thermal conditions, but with temperature of 300.15 Kelvin and CNT or copper as materials. So after the boundary conditions are done, we then move on to set the solution methods and residual monitors for the simulations. The solution methods are set as Green-Gauss cell-based, and as for the residuals, we change the absolute criteria to 1 times 10 to the power of -6 for continuity, S velocity, Y velocity, as well as energy. So after that, we move on to modify the solution initializations. So the parameters are set as standard initializations with 1.8 meter per second as X velocity and 300.15 Kelvin for the temperature. So after the initialization is done, we then change the number of iteration under calculation to 1000 and begin the simulations. The simulations procedures are repeated for different inlet velocity, different tube arrangement, different fin material, as well as different tube diameter.
I would like to present the comparison of experimental and simulation data for our fin and tube exchanger. The table shows the outlet temperature for both inline and staggered configuration at various flow velocity using 6.35 mm tube diameter with CNT composite fins. For the inline configuration, the temperature range getting decreased. Similarly, for the staggered configuration, our validation shows that the simulation result closely match the experimental data, maintaining an error margin below 10%, which is indicating our model are valid for the simulation.
So here is the velocity vector in tube and fin heat exchanger. We use different type of the flow rate condition, which is 1.8 until 3.8 meter cube per second. So from here we can test different flow rates to see how fast the fluid move inside the heat exchanger. So here is the contour of velocity in tube and fin heat exchanger. Also we use the different flow rate from 1.8 until 3.8 meter cube per second. So here we can test how flow rate affect airspeed inside the heat exchanger. So this is the contour of temperature in tube and fin heat exchanger. The flow rate condition that we use is 1.8 until 3.8 meter cube per second. So here we can testing how flow rate affect cooling inside the heat exchanger. So this is the inline tube arrangement. So from here we can see the velocity contour, velocity vector, and also the temperature contour from the inline tube arrangement. So this is the staggered tube arrangement. We can also see the velocity contour, velocity vector, and also the temperature contour. So here we can make the comparison between the inline tube arrangement and staggered tube arrangement, and we can finalize our heat exchanger design. So this is the effect of fin material, which is copper. So here we can see the pressure contour, velocity contour, temperature contour, and also the velocity vector from here. Copper fins efficiently move heat away from the tube, which is high thermal conductivity, and this allows for faster cooling of the fluid, which is at a lower outlet temperature. So here is the effect of fin material CNT. We can see we can make the comparison between the CNT and the copper here. So CNT fins are even better conductor than a copper, which is much lower outlet temperature. Also, this allows for even faster cooling and potentially smaller heat exchanger design. We can make the comparison from the analysis here. So this is the effect of tube diameter, which is we choose 6.35 mm. We can observe the pressure contour, velocity contour, temperature contour, and velocity vector. So from here, the smaller the tube size, the cool better at the lower outlet temperature due to the larger surface area. But may occur the higher pressure drop and more friction can occur.
Now, I will be presenting the key findings from our CFD projects. I will quickly walk you through 8 important graphs. Let's begin. Heat transfer coefficient versus velocity. Figure shows that the heat transfer coefficient increasing with velocity for 3 different tubes with 12 mm diameter in an inline arrangement. Higher velocities improve convective heat transfer, enhancing the heat transfer coefficient. Pressure drop versus velocity. Pressure drop rises with increasing velocities. This is due to greater frictional forces within the fluid flow, indicating higher energy cost for pumping as velocity increases. Heat transfer coefficient versus tube diameter. Smaller tube diameters such as 6.35 mm have higher heat transfer coefficient due to greater surface area to volume ratio. This is critical for maximizing heat transfer heat exchanger efficiency. Pressure drop versus tube diameter. Higher pressure drop for bigger tube diameters, highlighting increasing flow resistance. This trade-off between transfer efficiency and pressure drop must be carefully managed. Heat transfer coefficient of different tube arrangements. Inline arrangement showing higher heat transfer coefficient. This is because inline tube create more turbulence, enhancing heat transfer. Pressure drop of different tube arrangement. Inline arrangement results in higher pressure drop due to increased turbulence and flow resistance. Heat transfer coefficient of different fin material. CNT fins have higher heat transfer coefficient due to better thermal conductivity, making them more efficient for heat transfer. Pressure drop. The difference in material properties affect the pressure drop, impacting the overall efficiency and operational cost. In this case, copper and CNT are equal level in pressure drops.
By comparing experimental data with CFD simulation, it is evident that the Stark's configuration consistently yields more accurate prediction of outlet temperature, showcasing its superiority over the inline arrangement. However, the cost implication and manufacturing challenge associated with CNT production underscore the need for a comprehensive evaluation of cost effectiveness and practical feasibility before implementing CNT fins in heat exchanger application. The trade-off between performance benefit and associated costs emphasizes the importance of a balanced approach in selecting the optimal fin material and tube arrangement to achieve efficient heat transfer while considering practical constraints for successful implementation.